d's, and then you can do f of xx and f of xy. I got caught up on that.
Oh, all right. So let's talk a little bit about that. The first derivatives are pretty clear, right? So when we say f sub x, that's partial of f with respect to x. F sub y is the partial of f with respect to y. Now the tricky part is what happens when you start doing double derivatives. So you have f, the xx is pretty straightforward, but what you need to know from the Leibniz notation is that this is taking the derivative of f with respect to x. So that's essentially this thing or this thing. And then you're going to take the derivative of that with respect to x. So in this particular scenario, the notation that they come up with is that this is d squared f over dx squared, which is very similar to what we have before with the regular derivatives. And similarly, fyy is d squared f and then dy squared. But now when you start talking about mixed partials, so this is the derivative of f with respect to x and then with respect to y. So in that order, what you have to think about here is that this is the derivative of f with respect to x. That's the first one. And then you're taking the derivative of that with respect to y. And so when they put this together, this is going to be your d squared f divided by, and then now they write this in the order that it's written, dy dx. And so what you can try to remember is that if you're looking at this fxy, this goes from left to right, left to right, left to right, left to right. Whereas this one, the one on the right side goes first, so it actually goes from right to left. So similarly, if we have dy or f of y or f sub y x, that means you're going to take the derivative of the function with respect to y first, and then you're going to take the derivative of that with respect to x. So this is d squared f and then dx dy. Again, right to left. So it's tricky. It's kind of lame in the sense that most of the functions that we're going to be dealing with say that the mixed partials are equal anyways, so it's not that big of a deal. But but the notation is still important. This can even get extended to 3 variables if you have f of x, y, z. So if you want to take the derivative, the third derivative, so the derivative of this with respect to x and then with respect to z and then with respect to y. So the third derivative, again, there's going to be 3 derivatives that's happening here, is that you're going to write this backwards essentially. So dy, dz, dx. Actually, before I do that, why don't I lay it all out. So we want to first take the derivative with respect to x, so df dx, and then from here you're going to take the derivative of this with respect to z, that's the second one, and then from here you're going to take the derivative of this with respect to y, that's the last one. And so now you can see where all these pieces of the notation comes from. So the partial, there's 1, 2, 3 d's of f, and then dy, dz, dx. So if you just remember that they're opposites of each other, they go backwards, then that's all you need to remember. Okay, so that's a good question.
Thank you. That clears it up a lot because I wasn't even thinking about that. But when
Yeah, and a lot of times we just stick with the subscript notation, which makes sense to us. It's easy, it goes from left to right, and it's not an issue. And so if we have a choice, we generally use this because there's less writing. But sometimes the other one pops up, and then we have to know what that means. Okay, cool. Any other questions? Question number 12 of the exam. Which part, the web sign or the proctored? Proctored, number 12. Triple integral. Let's see. What can we say about this? Finding limits in Cartesian coordinates. I don't I don't remember.
if
Oh, I
it
go
looks,
ahead.
if it's the one that I'm thinking of, it looks a little bit like either a ramp or a cheese wedge.
Oh, okay. So let me do a random one. It's okay. Let me see if I can pull up a random problem. I think I got some of these from the book Cheese Wedge. So the idea is kind of like the quiz, I think, and that is to look at a shape, a particular shape, and then see if you can come up with the limits of integration. So this would be multiple integrals, and we would be looking at something. Change of variables, sphericals, evaluating. I think it's, we have some examples here, triple integrals. Or is the cheese wedge? Maybe it's in the actual, not the applications. The integrals. Now we could use any of these, but let's see if we can. Well, this look interesting. All right, cheese wedge. Let's do a region. So let's do a circle. circle radius 1, and let's do a plane here. X plus y, maybe. 0 to pi. Does that look like a cheese wedge? Ooh. Oh. Let's add 1 to this. Well, not exactly a cheese wedge that I was thinking of, but I know how to make it a cheese wedge. Let's get rid of x. And let's bring it back down. There you go, something like that. So the idea is that if you're looking at this, and I don't know if you have I forgot if the picture was animated or just a still picture, if there was a picture. Um, hmm. All right, here we go. So the idea is to see how this would work in for triple integrals, and you generally want to decide what you want to integrate with respect to first. And for most cases, I think you want to integrate with respect to z first. There's some very special cases where it might be easier to integrate with respect to another variable first. But let's say you're going to integrate with respect to z first. And how are we going to do that? Let's see. What if we draw a line parallel to the z-axis? So that would be going straight up. And then what we have to do is like imagine this thing is going to go and hit the bottom of that. So if this thing is not something that you yourself can turn and twist around, you have to imagine what's happening. And then, so to find limits for z, you're going to have to imagine that this thing is hitting from the bottom, and you have to figure out that the bottom is actually going from 0, and then it's going to hit this top part before it goes out. And the top part is that plane. I think it was z is equal to y. So let me label this plane z is equal to y. And then from here, you look at what's left. And then if you look at the xy plane and draw the xy plane like an xy plane, then you have the semicircle. I think we agreed that this was a circle. And then now you can decide what to integrate with respect to first. You want to integrate with respect to x or y first. And so I think it'd be easier to integrate with respect to y first, draw a line parallel to the y-axis. So y, we go from 0 to this top part of the circle. Now this top part of the circle is, you need to write it in terms of y. And then you need to decide whether it's positive or negative. And since this is on the top part, this must be the positive portion. So that's going to be your limit, the positive square root of 1 minus x squared. And then x will be constants. And then you have to remember that this thing starts from -1 to +1. So this would be one set of limits that you can choose. Now, for this particular problem, and it looks like you're talking about cylindrical coordinates. For this particular problem, you can actually do cylindrical coordinates as well. So in cylindrical coordinates, let's make a note here, cylindrical. In cylindrical coordinates, you're going to have a z, an r, and a theta. So the z is going to be the same thing as in Cartesian coordinates. So the z is going to be the same thing in Cartesian coordinates, except you need to change your x's and y's into r's and thetas. So instead of a y, so this is still 0, but instead of a y, you're going to say r sine theta, because that's y equals r sine theta. And then now you look back at the picture, the shadow that you have on the xy plane, and just express that in polar coordinates. So the r limits go from 0 to 1, and then the theta go from 0, and it just stops at pi. So you can also write this in cylindrical coordinates by doing the z first, examining the z first, and then what happens on the xy plane with r and theta. Okay. So is that part okay? Okay. More interesting. So this you can do both. You probably don't want to go circle coordinates here because it looks more like a cylinder. But if I change the region, so that there's like a hole inside, kind of like that pineapple problem in that quiz, then you can't, I mean, you can, but you wouldn't be advised to use, what's that called? Cartesian coordinates anymore. This one definitely should use cylindrical coordinates. Let's see if I can get a good picture of this. So it's not impossible to do this in Cartesian coordinates, but you might get stuck with having to do like several integrals, and that's going to be more work than it's worth. So let's make a note here saying this would be cylindrical coordinates only. And then, so that's the thing, is that we won't do y limits. We'll still do the z limits. Is still z is equal to y, but y is still equal to r sine theta. But now, instead of x and y, I'm going to write it down, but I'm going to cross it out and saying no Cartesian, because it's going to be too hard. Cartesian, that's right. So go straight to cylindrical coordinates, and what happens here, the shadow on the xy plane, if we look at the original drawing again, well, you can see it here. So the shadow on the xy plane is just a one of these annulus things. So your z is still going to be from 0 to y, which is r sine theta. But then your r is going to go from 1 to 2, and then your theta is going to go from 0 to pi. Okay, so in the last problem, we got the y limits from this semicircle up here. And then that semicircle, well, at least the whole circle is x squared plus y squared is equal to 1. The semicircle is y is equal to either plus or minus, but we notice it's in the top, so it's going to be the plus square root of 1 minus x squared. So that's how we got the y limits. And if you were to do this integral, your y is going to involve this square root of 1 minus x squared, which is going to be kind of tough. So it's probably easier in cylindrical coordinates, but it's still, we can still find it in Cartesian if we had to. And it's, in this example, it just says it's really hard to do it in Cartesian, so go cylindrical. Question?
So when you use the y integration, you don't go like through the solid, you go like touching the the y-axis to get that
Yeah,
integration?
so when you get the y integration, you ignore the three-dimensional picture. You only look at the shadow that it leaves because you took care of the z already.
Mm-hmm.
So once you take care of the z already, you ignore that, and then you just look at the two variables that are left, which is x and y, and you try to see what happens on the xy plane.
Oh, I see. That's what got me messed up.
Yeah, so
Yeah.
on the xy plane, it's just a two-dimensional picture that you're looking at, and then you ignore the three-dimensional picture.
Oh, okay. All right. Thank you. Got it.
Okay. All right. Anything else? Any other questions?
Sorry, just to clarify again. So when we're looking at, so for example, we're looking for the limits of integration for the y's. Do we draw a line parallel or perpendicular to the y? Or yeah,
Parallel. So when
parallel
you're
to the
finding
y.
limits, yeah, when you're finding limits for a particular axis, for a particular variable, you're going to draw a line parallel to that variable. So if you're starting off in 3 dimensions, then your line's going to be in 3 dimensions going into the solid. And then once you got that 1 dimension out of the way, then you're down to 2 dimensions, and then you just focus on a 2-dimensional picture.
But then, for example, like for the y, it goes from 0 to the square root of 1 minus x squared. If we draw, if we draw the line parallel to the y, how are we going? How is it that we're seeing that we're coming out of that square root 1 minus x squared if we're going? I think I'm confusing myself.
Okay, what if I tried to do it a different way? Let's see if this will help. I hope it'll help and not confuse. So I'm going to redraw that picture here. X and the Y. And then this time I'll do it in, let's see, I'll try to select an orange color. Now, if for some reason you decide you want to do this in terms of X first, and then Y, then you would draw a line parallel to the x-axis from left to right. And then you need to figure out what these functions are. Now, this is going to be more difficult because you're looking at it kind of sideways functions. So I need to write my x squared plus y squared plus or is equal to 1, I need to write that with x by itself as
Right,
a
in terms of
function
like,
of y.
right.
So that's not the difficult part. The difficult part is that in this case, I would need to consider the plus and the minus. So it looks like I will enter here through x equals negative
Negative.
square root of 1 minus x y squared.
Mhm.
So negative square root of 1 minus y squared. And then I would be inside of my region, and then I will exit through the positive square root of 1
Oh,
minus y
okay.
squared.
Right.
And so if you do it with respect to x first, that's what you'll need to do. And then you come out of that, and then now your y limits are constants. That's just going to go from 0 to 1.
To 1.
Yeah. So so if you're whatever you're finding the limits for, as long as it's not the last limits, because the last limits are always constants.
Right.
If you're looking for limits of something, you would draw a line parallel to that axis. So parallel to the x-axis would be a line going from left to right.
And then you just follow the line to see what functions you're going in and out of.
Yes. And
Okay.
the function you need to write a function where x, whatever the variable is equal to something with the y, the other variable, in this case, the y.
Right. Right,
Yeah.
right, right. Okay. Yeah. Okay. I think that's making more sense.
Okay, cool.
Okay.
I'm glad
Thank
you
you.
pursued that. Uh-huh.
Yeah, because I think what I've been doing is I've been drawing the line perpendicular to the axis
Ooh.
and moving that whole line across the axis, if that makes sense.
Oh,
Which I guess
yes,
is
yes.
kind of the same thing, but
Yes, it does make sense. So I
yeah,
think,
but then I would get confused because that line would hit like several functions sometimes depending on, what
right.
we're looking at. So
Yeah, that's the tricky part. So let me see if I'm getting what you're saying. So you're saying you're drawing these lines going across,
right,
which is also correct, but then you have to figure out the starting point where you're starting.
exactly.
Yeah, so I think that's it's a way to look at it. The way the integral works, you're kind of slicing it,
Hmm.
and but the tricky part about that is that you're not easily. I mean, you could still do it, but you're not easily establishing the where you're going in and where you're getting out of.
Right, right, yeah. And I
Yeah.
think that's where I would get confused. Okay, cool. That makes sense. Thank you.
All right. Awesome. Cool. Any more questions? Coming out some good questions here. I wanted to ask if anybody tried to access the videos from the last couple of days, if we're still having issues with that.
Yeah, I
I'm
just
still
checked again just now, and it's still asking for like a password or whatever.
okay.
Yeah,
And
I
those
mean,
passwords, do you know if those passwords are working?
oh, did you put some out? I didn't even try any of them.
No, well, I didn't put it out. I don't know if you can
I tried guessing, but I didn't want to like mess something up. Like,
guessing. Oh no. So in Zoom, cloud recordings, and like yesterday's. Wait. So I can easily get to it. It seems like it.
once you click on the videos, when it asks you for the,
Oh, well, it's not asking me because these are my videos.
oh, yeah.
So what I want to do is if I go to the meeting and I click on this, and so the password for yesterday's, if you guys want to try this,
I don't know if that's
from
just for the meeting
414.
though, but let me try.
So the password is, there's no space here. It's 413061.
Let's see. 413061. Access recording. No, that doesn't work either.
Doesn't work.
That was for yesterday, right?
That was for yesterday.
Yeah, that didn't work.
What does report mean?
Because I
Report.
think that's the password like for the actual meeting.
Ah. Shoot. Okay. I'm going to see if I can ask somebody about it.
Yeah, it seems to just be this week where it's doing that. So
Yeah,
just yesterday.
it's since Zoom updated their their program and policies and stuff from the Zoom
Right.
bombing things. So I need to ask our IT person. All right. Anything else that we need to talk about? Discuss?
I feel like I'm dominating these past two meetings because I've been asking all the questions.
No,
But
yeah, go ahead.
if nobody else has anything they want to cover, I was thinking maybe we could cover local maximums and minimums and how they relate to gradients.
And how they relate to gradients.
That was another thing that caught me up.
Okay, let's see. Max and mins, how they relate to gradients. So for this, let's take a look at the book, maybe.
It was one of the true false questions from the book about gradients and local minimum.
Well, the only thing I can think of is that, let's see, when we do local max and mins, I guess that's in the previous chapter, we're always talking about the critical points, and this book for some reason does not make a big deal about critical points, but but the critical points are when the first derivatives are equal to 0, and I think that's about the only place where the gradient can possibly come in. I'm just trying to get to the gradient vector. That's not what I wanted. Well, in any case, let's talk about the second derivative. Well, let's talk about gradient. So for this, we are, so if something's a local max and min, whoa, why is it all pink? So local max min means that something's a critical point. And then a critical point means that fx equals 0 and fy equals 0. So the only thing I can think of in terms of relating this to the gradient is that this turns out to be the components of the gradient, which means if they're both equal to 0, then local max and min mean that the gradient has to equal to 0. And it's a 0 vector, so you would need to make sure that that vector had an arrow on top or is boldface or whatever. And I don't know exactly what the true-false question was asking.
It's only the 0 vector that has one number. Every other vector has 2 because it's a vector.
Say it again.
So it's only the 0 vector that is 1 digit, just like the 0 and the arrow, and the rest are denoted with like the brackets and then the number, comma number, bracket.
Yeah. So you can write it 0, 0 as a vector, or you can write it 0 with an arrow on top as a vector.
Yeah, they're equivalent expressions, right?
Yeah, these two are the same. They're equivalent. And what else? What does that mean? Oh, I'm trying to process your question, Stephanie. I don't quite understand.
Are you talking about like unit vectors, Stephanie?
No, there was a question about if f of x and f of y were 0, what's the gradient? So, which I think this is, at least that's what I think it was. I don't quite remember. I took it.
Oh, so maybe there's another question where, so by the way, the arrows here are important. So bottom line from the above here is that if P is a local max or min, then the gradient at P is equal to 0, and that's a 0 vector. Now, the backwards does not necessarily hold true. So by the backwards here, I'm going to do this in a different color. If gradient of f at the point P is equal to 0, then P is a local max or min. So this is not true. So not true. So if it's not true, then there must be a counterexample. You know what the counterexample is? Or you know what one possible counterexample is? Anybody?
Is it the absolute max min?
No. So think about the second derivative test.
Oh, saddle point?
Saddle point. P could be a saddle point. So the way they state things, the if then in math, they're really precise about how things work. So so the if then statements doesn't interchange in math. So if they say if and only if, then that interchanges. But when they say if something, then something else, the backwards of that may not always be true. And so the backwards of that is called the contrapositive, and that's not always true. And here's a perfect example of that. So if P is a local max or min, then the first derivatives are 0 or the gradient's equal to 0. So that one was one of the theorems that we saw. But if the gradient is 0, does that automatically mean it's a local max or min? And that's not true. And so it's not true here because it could be saddle point. Back in Calc 1, it's also not true because it could be one of those inflection points like the x to the third power. So that's why it's not true. 14.7. Cool. All right. So good question. Anything else popping up? number one. So number one. Oh, describe functions of several variables. I don't know. Look at my suggestion for like the first couple, or maybe the ones with free responses. I generally got those free responses from the concept check in the book. So if you look at the concept check in the book, if you look at the ebook from Webin, you can actually pull down answers. So you could check that and get the answers and see if you can make sense out of it. And then that's basically what you have to say. So basically a function of several variables takes, several variables as an input and gives a real number output. And then I think in the answers that they have, they describe how to graph it and stuff like that. So functions of 3 variables, then you'll take, 3 values, x, y, and z, you put it into this function, and then you get a unique output. So an example or application would be, I don't know, maybe your grade depends on only 3 things: exam, quiz, and homework. Then you can say that your final grade is a function of 3 variables. And I don't know if I don't know if they ask about the graph of that too, but again, you can look at the concept check in the textbook, in the online textbook, to see what they say. But that's generally what I'm looking for. It's just explaining that, a function is something that takes an input and gets an output. You just have to be specific about what the input is, because if it's 2 variable, then I'm looking for an input having 2 numbers. And if it's 3, then I'm looking for 3 numbers. Okay. Anything else?
Can it be like the gradient of 3 variables as an application?
It kind of is, but it kind of is not, because when you talk about the gradient, that relates to a function that you have already described. So the functions of 2 variables, I think it's a little bit easier to come up with an example, because they have, one example that we use in particular, and we used it quite a bit, I think, was the wind chill factor. It takes the speed of the wind and the temperature, and then makes, so those are the 2 inputs, and then you get an output. So something in 3 variables, you kind of have to make it up, and maybe instead of wind chill factor, you can think about a temperature or something like that, a temperature of something in 3-dimensional space. So the input could be the x, the y, and the z coordinate in space somewhere, like in a room, in a house. And then the output could be the temperature at that very single point. And there's some other weird ones where you have an x and y like just on a plate, and then at certain times of the day would be your 3rd variable, could be time or something like that. So so function of 3 variables, if you have to come up with an example, for me the easiest is like your grade is based on 3 things, and then your output, so that's the input, and then your output would be your final grade. So or you can get creative and find some other interesting applications. but that's generally what it is.
Or can I use level curves? That's also 3 variables.
It's 3 variables, level curves. So the input would be, that one's still kind of difficult to use because your input has to be 3 things, and you can think about 3 points, and then your output is a number that comes out. And so it's hard to describe that as a level curve, or it's hard to describe a level curve as something like that. So I don't think that'll work either. A level curve, usually it's when we think of level curves, it's where we know that the function already exists, and then we're coming out with a level curve. So I think that's the same thing as the gradient or the partial derivatives, is that the function has to exist first. So I think the example and application that I would be looking for would be like an actual application, like temperatures or volume maybe. Yeah, or another example of a function of 3 variables could be if you're given the base, the width, and the height. So that's 3 variables, and then your output could be either the volume of a box or the surface area of a box or something like that. So that would be another example that would be of 3 variables, because it takes a base, length, and width or something.
Oh, okay.
Okay.
Okay. Thank you.
Alrighty.
I'm still confused about the question, the problem we were talking yesterday, number 10.
Which one was that?
Finding the maximum and the minimum values.
From?
It's a level function, and it has a ellipse in it. Yeah, like.
Oh, so the problem that we were looking at yesterday, I think what you need to do is you need to take a look at the levels themselves, because I think instead of a -2, it was a +2 or something like that. So that doesn't correspond properly. So if you look at the answers, and if you look at the picture where the answers came from, I think
Because I found 2 minimum values and 2 maximum values.
right, but I think I only in the choices I only selected 1 maximum and 1 minimum,
Right.
and the other one is not a maximum or not a minimum.
Oh.
If you look at the z values of those points that I was describing.
Okay, see. So which one is the one you said that you wrote incorrectly? This one or the other one that you had to find the limits of y and z?
I think the one that I didn't do correctly had something to do with it was a multiple choice where it should have been multiple answers. So there's a difference there. So the one that I didn't write correctly was because I didn't select the right type of question, but I fixed that already.
Oh, okay.
All right, anything else happening? So tomorrow we're going to have a regular class. I'll send an announcement in in a Zoom thing. So hopefully you'd be kind of done with your exam already. If not, you still have, I guess, the end of tomorrow for one of them and then Friday for the other one. And yesterday I looked, there were still a lot of people that have not taken the first attempt. So I'm hoping you guys take advantage of the multiple attempts of the test.
Is it going to have the same questions the second attempt, or is it going to be different questions?
It's similar, but it's not exactly the same. Like for example, let's see, maybe one attempt you would have this graph, another attempt you would have, a different graph. So it'll probably be different. It's not like WebAssign where you just change numbers. It might actually look, the drawing itself would probably be looking different. Okay, Chris.
Okay. I see.
Yeah. I mean, it still might be the same. It just kind of randomizes the selection.
All right.
All right. Are we good? We
Right.
good? We good? Okay. So I think maybe now might be a good time to sign off. I'm going to need to send an email to the IT person about the things, what do you call it? The videos that's recorded on the cloud, and see what I could do about those password things. All right. So we good? Any other questions before we cut out?
I'm good.
Okay. Cool. All right. I wonder if I'm going to do my lecture from the backyard tomorrow.
It looks nice out there.
Yeah, it's pretty nice. Except the sun's creeping on my computer now.
I'm gonna go take my third attempt. I think I'll see you tomorrow.
Okay, good luck. All right, guys. Thanks for coming. Thanks for participating. Good luck on your test, et cetera, et cetera. I'm going to end the meeting now. Bye.
Bye.